What I'd like to go to now is there's an example problem on vertical curves. I'm not going to go through the problem because it's very straightforward. Just like to make a couple of points, because this problem again uses slightly different nomenclature than what's in your reference book, but it's an example of the type of problem you might have on the exam. You have a 400-foot long equal tangent vertical curve. You have two tangents of minus 2.5% to a plus 2% upward. So this is going to be a sag curve, as you can see from the drawing there at the bottom of this particular page. This one says that the tangent intersects the PVI at station 426 plus 25. So in this problem, they're giving you the elevation of the point of vertical intersection, and they give you that elevation. They also tell you that the width of the paved surface is 48 feet, and the pavement has an average positive slope of 1.6%, or 0.016 feet per feet of run, and that's from the center line of the pavement out to the gutter or out to the shoulder, and that's so that the water will drain from the roadway out to the ditch line there. And if you go through, and I'm not going to go through the questions and the solutions on the next page, you can probably do that on your own. It's a very straightforward question. They're asking you about lengths and elevations and where the high point and the low point is, and if you can just keep track of, again, we've got to convert these distances to stations, because that's what all of our equations are written in. And if you can just simply work from your knowing what your distance is and your grade, you can compute all of these elevations very easily. One caution that I probably ought to give you is that in this particular problem, when you have sag curves, if we're working off of grade 1, which is the one on the left side that's going down, notice that the roadway is above the grade line. So when we compute these values of y, or offset, we'd be adding to elevations for sag curves where we subtracted for elevations with the crest curves in the previous example. I'd like to move to section 7 in your reference book, and that talks about speed parameters. And this really gets into some questions that you asked earlier, and some things that, well, some other things as well. And it's very complicated in highway design and highway analysis. Is there's a bunch of different speeds that we're interested in, and they're defined here on this particular chart. We have running speed, average spot speed, overall travel speed, operating speed, design speed, and average highway speed. There are a couple of these that are important, one of which is down near the bottom, design speed, and that's a speed that we're selecting for design of the highway. Interstates, we mentioned, are typically designed for 70 miles per hour. Our rural two-lane highways, if we're designing one now, we would design probably for at least 60 miles per hour. Urban highways maybe for 40 or 50 miles per hour, different speeds for different conditions. But that really defines how much sight distance we have to have and what our horizontal curvature and our vertical curvature can be for those particular roadways. The other speed, we have average, we have operating speed and average spot speed. And operating speed is really a speed at which drivers travel on a particular section of roadway, favorable weather conditions, and in a safe manner. And that's generally the speed they'd be driving, and speeds that we would set speed limits for on a particular roadway. The others, different definitions of speed, and they're used for different things, but not all that important in this particular setting, I don't think. We talk about design speeds, and if you'll notice in what's Section 8, when we talk about design speeds, that most of our design speeds are design elements, and by design elements, horizontal, vertical curvature, roadway width, etc., depend on design speed. And the way they depend on it is that we have to have certain stopping sight distance for certain speeds. The definition of design speed is it's the maximum safe maintainable speed under design conditions, which is, you have to remember that design conditions are wet pavement, slick tires, unalert driver, and a very small object. So the maximum safe speed under those conditions is probably much less than what most people feel comfortable driving when the weather is dry or the under good conditions, which occur most of the time. The design speed that we would use, it varies by type of facility. We use different design speeds for freeways versus city streets. By traffic volumes, we'll typically pick higher design speeds for higher traffic volumes. And by terrain, we typically would use different speeds for flat terrain versus mountainous terrain. And economics really comes into play in that, as well as driver expectancy. Now there is a chart in your reference book on page 16-7 that shows different design speeds by type of facility, type of terrain, and average daily traffic. And you might notice there on page 16-7, right in the middle, that it shows for freeways and level terrain, we would design for 70 miles per hour in rural areas, 60 miles per hour in rolling areas, and 50 miles per hour in mountainous areas. So those would be values that we would use for design. Okay. Now, Section 9 in your notes talks about volume parameters. And these particular parameters that are given in that part are primarily used for planning. Because when we're interested in planning or designing a roadway for 20 years in the future, there's some things that we need to know. And they use some parameters there. The first one, ADT, are the average daily traffic on a particular facility. And it's simply a 24-hour count taken over a number of days, an average, to get the number of vehicles that use a particular roadway per day. We design, though, based on hourly volumes. So DHV is the design hourly volume that we're going to design for, and that really tells us how big the facility has to be, or how many lanes that we have to provide to handle that particular volume level. And this K ratio, or K factor, is the ratio of the design hourly volume to ADT. And typically we're looking at that being about 0.1 to 0.12 there. The directional factor is the percentage of the traffic in the dominant flow direction, because on most facilities everybody goes into town in the morning and they go out of town, go back home in the afternoon. So it's not a 50-50 split on a roadway, and we need to take that into account. The directional design hourly factor is shown there next. Then we have something that's called a design capacity. We know that there's a certain volume, or a maximum volume of traffic, that a particular roadway of a certain size can handle. And that's called the design capacity of that particular facility. And then MSF is the maximum service flow rate under ideal conditions. Because typically in highway design we start out with ideal conditions, which don't exist, but that's our ideal conditions, and then we begin to adjust that ideal capacity downward to account for those conditions that aren't ideal. And I'll show you some examples of that in a few minutes. Okay.
The design hourly volume, is that a average or is that a peak volume?
The design hourly volume, what we what they typically do is they take the hourly volumes for every hour during the year. Okay, and we typically design for the 30th highest hour in the year's time. Okay, and the reason for that, if you're here in College Station, we have about 5 weekends a year. We have football games here, and those have really high volumes. We can't afford to build our roadways to accommodate that, so we'll drop back down that curve. But it's the 30th highest hourly volume on that particular facility is generally what we will design for, and that typically would equate to a typical peak hour in that particular locality. Okay, so it's a peak hour volume, morning peak or afternoon peak, but for a typical day during the year rather than the absolute highest hour during the year. Okay, and typically the type of problems that you will get dealing with these variables is they'll give you the average daily traffic and a set of factors and ask you to convert it to a design hourly volume, or they will give you a design hourly volume and ask you what the average traffic is for a particular day. So you work back and forth with these particular values. We talk about, I mentioned ideal conditions don't exist, but that's sort of our starting point. The other thing that we need to understand in traffic analysis is a concept called passenger car equivalence. And really, when we look at a highway facility, we have cars, we have trucks, we have buses, all different types of vehicles that use it, but we need to convert them all to some common units so that we can talk about different facilities sort of in the same breath. And we convert everything down to the lowest common denominator, which is what we call passenger car equivalence. If you notice that table there on the notes, when we say the equivalent for a bus is 1.5, what we're really saying is that in our accounting scheme, that every bus that we have on level terrain is the equivalent of 1.5 passenger cars. Reason being, they take up more space, they have slower acceleration characteristics than passenger cars. So if we could get rid of 2 buses, we could accommodate 3 vehicles on that particular facility. So when we look at traffic streams that have certain percentages of passenger cars, certain percentages of buses, certain percentages of trucks, we convert that mixed stream to some equivalent number of passenger cars. And those are some factors that are there. There's equations that you can compute those with, but you notice that it varies by type of terrain, and that in mountainous terrain a truck is worth 8 passenger cars, whereas in level terrain it's 1.7 passenger cars. Reason being, on long upgrades they tend to lose speed. Not only are they physically longer, but they introduce gaps in the traffic stream which take up more space as well. So it's an accounting scheme to convert everything to some common denominator. Okay. Now in section 11 we talk about the concepts of capacity and level of service. And capacity is defined as a maximum flow rate under prevailing conditions. And it's a very simple concept. A roadway has a finite amount of capacity, or a maximum number of cars that it can accommodate under the prevailing conditions, and it simply can't accommodate any more than that. And that's a number that we can calculate. I shouldn't say different facilities have slightly different capacity rates. There's another concept that's called level of service, or LOS. You'll see it written some way, and it's a methodology or mechanism for really quantifying quality of service on highways. Okay, how good or how bad a particular facility is working. Now for freeways, it's defined by the density of vehicles on that particular facility. And the units are passenger cars per mile per lane. Okay, so we can quantify how good or how bad it is. And level of service varies from level of service A to level of service F, where A is free flow and F is stop and go or congested conditions. And it's a very similar concept developed based on grades you get on your report cards. A is very good, F is very bad. And generally you think of in highway transportation circles that E really defines the capacity of a roadway, and when you get past that, you're over capacity or you're in unacceptable conditions. In a lot of our large cities, that's a fairly frequent occurrence. Now, the curve that you see on the bottom of the page is a curve of average travel speed versus the density of a particular facility, or the volume per lane and the average travel speed in miles per hour. And there are some dashed diagonal lines on that where it has K is equal to 12, K equals to 20, etc. Those are densities for those different speed volume combinations. And you'll also notice that there's some letters there in the middle of that, A through F, and those correspond to the breakpoints for those different levels of service. Basically, level of service A, there's very few vehicles on the freeway. You can pretty much pick your speed, change your lane, no problems. As you move across that continuum and get out to levels of service E and F, you're getting to capacity or congested conditions. Your stop-and-go traffic, you can't change lanes, and that's really what we're looking at there. You'll notice at that particular curve that capacity is the point at which the curve turns down out there, and it's about 2,000 passenger cars per hour per lane on a freeway. That is the maximum that's defined by the 1985 Highway Capacity Manual. Okay, so if you had a one lane of traffic, it says you can handle 2,000 passenger cars per hour in that particular lane. If you had two lanes of traffic, then you could handle 4,000 passenger cars per hour on those two lanes facility. So a couple of points. These are passenger car equivalent values there, and this is also given in a per lane basis. And the other point to make about that is that it is ideal conditions shown on that particular chart. And those were freeway curves, and we're going to talk about freeway capacity, because we've talked about freeway capacity or capacity as being the maximum capacity under ideal conditions. And the C sub max is the mean service flow rate per lane for a given level of service, and these volume to capacity ratios for a given level of service, I there. And let me define a couple of terms there. Volume to capacity ratio is simply a ratio of the demand or the number of vehicles on the facility divided by the capacity of that particular roadway. And those subscripts you see in the equation are for different levels of service. So if you go back to that graph on the previous page, you'll notice that for, let's say, a level of service B, we would come out here to where level of service B ends, or that K equals 20 line, intersects whatever speed and number of lanes that we have, project that point vertically downward to where it intersects the horizontal axis, and we would read the maximum capacity, or the maximum capacity for level of service B. Okay. If we want to know what we could accommodate at level of service C, we'd simply move out to the break point for level of service C, project downward, and get a volume that we could accommodate for that level of service. So the worst worse level of service we're willing to accommodate, the more vehicles that we can handle on that particular facility. And you know, we can look at this particular chart, this equation there on the slide 12, and you'll note that on the graph in front there's volume to capacity ratios for different levels of service. Those are the numbers that are shown in parentheses at the bottom of that graph. And if we look at, we know what the volume to capacity ratio is, we know what the maximum service volume, service flow rate is, that's the number just above it, and we know what the capacity or the maximum capacity is going to be at that particular problem. Okay. Now, if we wanted to calculate the service flow rate, or the number of vehicles that we could accommodate, we would use equations that look like this for freeways. Okay, what we're trying to figure out is the service flow rate. We have the maximum service flow rate, M sub F sub I, for different levels of service. And let me explain what these variables are in the equation there. Remember, we talked about capacity under ideal conditions. Well, we've got to adjust for those things that aren't ideal. So that's what you see, all the factors there. The first factor, the capital N, is the number of lanes that are available for traffic. Okay, and then we have factors to adjust for lane width that may not be ideal. We have factors to adjust for the number of trucks and buses that are in the traffic stream, because those are going to limit what our capacity is. And then we have what's called a population adjustment factor there, and that particular factor accounts for whether you've got primarily commuters in your traffic stream, or you've got a lot of visitors or out-of-town people in your traffic stream. Typically, commuters would drive closer together than visitors would, and you could accommodate more vehicles if it's primarily a commuter stream there. So what we're doing there is adjusting. Now, if you think about what we're doing, if I could get back to me, we're starting out with some ideal capacity, which would be up here at this level, and then we're multiplying it by a set of factors that are not ideal. So we're really adjusting downward, okay, adjusting our ideal capacity downward. So all of those factors there are going to be some number 1.0 or less to account for non-ideal conditions. What are ideal conditions? It's 12-foot lanes. That 12-foot lanes would be ideal. All passenger cars would be ideal. All passenger cars on level grade, in fact, would be ideal, and that we would have all commuters or familiar drivers in our traffic stream. Okay. If any of those conditions are not met, then essentially what you have to do is either through an equation or through looking up a value in a table, plug the appropriate numbers into that equation and just adjust that ideal capacity downward.
So you said 12 foot is 1.0?
12 foot would be 1.0.
All cars, no
all
trucks?
Passenger cars with no trucks would be 1.0, and
Everybody.
all familiar would also be 1.0.
Everybody who lives here, 1.0.
1.0. Okay. And there's very few places where that's the case. So you're almost always going to have some downward adjustment there. So when we look at this, these values, we come into this equation, and we want to figure out what our service flow rate would be. Well, let's assume for a minute that we had all ideal conditions, and we had a 4-lane freeway. If you want to. If we have a 4-lane freeway and we want to, we have a volume to capacity ratio for level of service. Let me go back to my graph. So we have a level of service of,
What do you want, figure 9.1 on that sheet 11?
yeah. We go back to, let's say that we have a 4-lane freeway, and we have a 70-mile-an-hour design speed, and we want to design for level of service D. What we would have to do is, let's go to our level of service D line, which is this one that's right here that I just drew the red arrow on. We're going up to where it intersects the 4-lane 70-mile-per-hour curve, and it's real convenient because they all intersect at the same point. And then we would project vertically downward, if I could, to where it intersects the lines at the bottom. And at least the way that I drew it, it came out to be about a volume to capacity ratio of 0.9. Yours is a little higher.
Yeah, I got a little higher. I'm a little more optimistic. I got about 0.93.
Somewhere in the neighborhood of 0.9 to 0.93 should be the volume to capacity ratio, depending on how carefully you do the graphs there. If you knew the equations for those curves, you could actually calculate the exact point that you would work with. Okay. Now, if we go back to this equation, let's use 0.9 since that's a little bit easier to work with. Remember, we said that we have ideal conditions, so all of those three factors are going to be 1. And if we look at this particular equation, how many lanes do we have?
Said we had 4.
Okay, I said we had 4 lanes, but that's a trick question. Okay? That's a trick question, and it's one that will probably catch you on an exam if you're not real careful. Generally, when we talk about a 4-lane freeway, we're talking about 2 lanes in each direction. Okay, so there's 2 lanes for one direction and 2 lanes for the other direction. So N would be 2 in this particular equation because we express capacity or volumes by direction. So we talk about a 4-lane freeway, it's 2 lanes in each direction. An 8-lane freeway would be 4 lanes in each direction. Okay. We said that the volume to capacity ratio that we're designing for is 0.9 at level of service D, and our maximum capacity under ideal conditions, go back to our curve, is 2,000 passenger cars per hour per lane. So that would be 2,000 times 0.9 times 2 times 1 times 1 times 1, and that would tell us really that we could accommodate whatever that product is, number of passenger cars per hour at that particular level of service. So that may be what we would design for in that particular instance. Okay, and it's a fairly typical types of question that might be asked. We go on to section 13. We're talking about these relationships between speed, flow, and density, and it really gets into what we would refer to as traffic flow theory, because again we're going back to mathematics and explaining these things in terms of parabolas and equations that we can use to describe those. The 3 parameters that are usually used to describe traffic flow are the speed, the flow rate or the volume, and the density of traffic on that particular facility. And the curve that we looked at a few minutes ago, where we were looking at level of service, it had those 3 parameters in it. It was volume by speed by volume, but then we had superimposed on it the density values as well. And let me just talk about density. Usually is defined as the number of vehicles or per mile per lane. We have jam density, which is defined as there's some value which, when the density becomes a certain value, gets high enough that vehicles are really at a standstill on that particular facility, and that's called the jam density for that particular lane. And we can compute a speed for a given density using the equation there in the bottom of that particular, or in the middle of that particular slide. The speed for certain density is the free flow speed multiplied by 1 minus the ratio between that given density and the jam density for that particular facility. And I've got a graph in a few minutes that illustrates a few of these points to you. A couple of other parameters just to talk about and get familiar with is headway, or the time between successive vehicles. It's given in seconds per vehicle. And spacing, or the distance between common points on vehicles, front bumper to front bumper, rear bumper to rear bumper. Okay. Headway would be the time from the rear bumper of one car to the front bumper of the next. So that's the actual gap between vehicles. And spacing, between common points. Let me go back to that. Headway would be the time from when one vehicle passes a point till the next vehicle passes a point, and it would be a common point on the vehicles, front bumper to front bumper. We would have a gap between vehicles, which would be a lesser distance than that, or a lesser time. And just a couple of things about headway. We talk about a capacity of 2,000 vehicles, passenger cars per hour per lane. That translates to a headway of 1.8 seconds between vehicles, and that's 3,600 seconds per hour divided by 2,000 cars per hour comes up with an average spacing of 1.8 seconds between vehicles. So if you know what the volume is, you can compute the average headway between vehicles and vice versa. So there is that relationship. And if you know what the speed is, you can compute what the average spacing is between vehicles. Now the curves that I was talking about are shown on this slide, and they're on page 1611 in your reference guide as well. But these show the basic relationships between speed, flow, and density. And you'll notice the parabolic shapes that come from here for flow and density, and for speed and flow, and then the curvilinear shape for the relationship between density and speed. And there's actually a set of equations here that if you know what the jam density is for these particular curves, then you can begin to compute different points along these particular curves. And I think there's an example problem in your reference guide, but we don't have one here. This next graph that I have is not in your notes, but just again shows the relationship. Well, it is on page 1610. These are different freeway density flow relationships under ideal conditions. A couple of different conditions here, different jam densities and different characteristics for different freeways. And when you look at determining level of service, and this is primarily for freeways, I've mentioned a couple of times that it depends on the density criteria. but that criteria can vary depending upon the freeway's design speed. And in this particular chart, you see level of service, and you have different design speeds there, and these are sort of the thresholds or the cutoffs. For example, the cutoff for level of service D for a 70 mile per hour facility is 0.93. And so, Lee, your number 0.93 was very close to that. You did well there. But if you had a 60 mile per hour facility, you could only go up to a volume to capacity density. This says those don't look like density criteria there. Those look more like those are actually volume to capacity ratio values in that table.
Yeah, that's what we were picking off.
That's what we're picking off the chart there.
The
So
bottom of the curve.
just so you don't get confused, they depend on density criteria, but the numbers in that particular table are volume to capacity ratio numbers. And there's a corresponding density that goes along with those. But the point is that the slower the design speed, really it translates to a worse design, and so we can accommodate fewer vehicles at that given level of service on the lower types of design there. Okay. Now, typically, the types of problems that you would be given are something like what's on the next page of your notes there. And this is a situation. It's a very simple problem, but I'd like just to walk through it, because it's fairly common to see these types of questions on an exam because of their simplicity. You have a 6-lane freeway with 10-foot lanes and a 70 mile per hour design speed. It's passing through rolling terrain. There's a few sections that have grades greater than 3%, and they're less than a quarter mile long each. The clear distance between overpass abutments and roadside obstacles is 2 feet for roadside median edges. Directional weekday peak hour volume is 2,400 vehicles, and an average of 750 vehicles pass through the most congested 15-minute peak hour period. Traffic stream is 14% trucks, 8% buses, and 4% recreational vehicles. Now, that's a heck of a lot of information there to try and figure out what's important in answering questions. But let me show you a couple of things on the next page in working through the types of questions that you're likely to get. You'll note that at the top it says base your answers on the 1985 edition of the Highway Capacity Manual. And that's the document I showed you early on this evening. First question it asks is how many lanes of travel in each direction. Okay, if you go back, the very first sentence says it's a 6-lane freeway, which means there's 3 lanes in each direction. So it's a very simple concept, but you notice right there up front the first question that they ask you, just to make sure that you understand that. So when you have 3 lanes of travel in each direction for a 6-lane freeway. Says, what is the approximate service flow rate? Okay, and this is a point that I didn't really bring out earlier, but service flow rate during the peak 15 minutes, when we're talking about a service flow rate, we've got some period of time within the hour when the flow is at highest amount, and we'd like to express that peak flow rate on an hourly volume. So if it says the peak flow during the hour is 750 vehicles for a 15-minute time period, if we wanted to express that as an hourly volume, we'd simply take 750, multiply it by the number of 15-minute periods in an hour, or 4, and get 3,000 vehicles per hour. That's the maximum service flow rate. The peak times the number of intervals during the hour that peak occurs. So that was given to us in the problem. And that's a very significant point in capacity analysis, is the difference between a flow rate and an hourly volume. Flow rate is some peak peak flow during an interval that's shorter than an hour in duration. And we want to convert that peak flow in 15 minutes to an hourly volume. We'd simply multiply by 4. If we had a peak flow in a 5-minute interval that we wanted to convert to an hourly volume, we would have to multiply by 12. Or a peak flow in a 30-minute period would have to be multiplied by 2 to convert it to an hourly volume. Okay. It asks us to compute in Part C the approximate heavy vehicle correction factor, because we have, we've got heavy vehicles, trucks and buses in the traffic stream, and those are not ideal. Okay, and that factor is counted. You notice that the first thing we have to do is go to the table and look up what the passenger car equivalents are for trucks, buses, and recreational vehicles. And the other part given in the problem is it was in rolling terrain. So we go to the table back a few charts ago, and we'd find that the passenger car equivalent for trucks in rolling terrain was 4. For buses, it's 3. And for recreational vehicles, it's also 3. Okay. So now we know what the equivalencies are, and we would substitute into that equation that's shown there towards the bottom of the page. It's 1 divided by 1 plus, and in that equation, P sub t is the proportion of the traffic stream that's trucks, and that was given as 14% or 0.14 in these equations. And then E sub t minus 1, that's the truck equivalency minus 1 or 4 minus 1. And we'd simply go on through the rest of that equation. So the real key here is to take that 14% trucks, convert that to a proportion or 0.14 in that equation, and to look up the correct truck equivalency factors or passenger car equivalency factors in the table for the right terrain for this particular problem.
Now, what does that 0.6 really mean? I mean, it means take the total number of people coming past here and multiply times 0.6 for an equivalent number of cars, or?
Where's the 0.6 that you're talking about?
The F sub HV.
The F sub HV is really a factor to adjust that ideal capacity downward.
Okay. That's right. I remember.
So what we're really saying there, that 0.6 that we're solving for, 0.602, the answer that we get is because that we have that all of those large vehicles in that traffic stream in rolling terrain, it can only handle 60% of the number of vehicles that it could if they were all passenger cars. So if we're just counting vehicles, we're only going to get 60% of the vehicles that we could if they were all passenger cars. Okay, and that's what that particular factor is going to be. So, again, you're likely to see a question like this, and the real key is, if you can look up the right number in the table, is to remember that the P sub t's, P sub b's are really proportions in that equation, and the data is usually given to you in terms of percentages. Okay. Now, if you get a number that's greater than 1, you know you've made a mistake in your calculations there. It should be something between 0 and 1.0 as the boundaries for that particular equation. Okay. Because it's always going to be 1 divided by 1 plus some relatively small number in that equation. If you don't have any buses or recreational vehicles in your traffic stream, those last two numbers in that string simply turn out to be 0. And it becomes a very easy problem to work with. Part D of that problem says, what is the approximate volume to capacity ratio? Okay. Now, what we know for that, that's really a pretty simple problem to work. because volume, we know what the volume is. We saw that over in Part B. The volume is 3,000 vehicles per hour on that particular facility. But let's look at the answer to that. It says from the Highway Capacity Manual, Table 3-1 for a 70 mile per hour design speed, the maximum capacity under ideal conditions is 2,000 passenger cars per hour per lane. You can also get that from the graphs that are in your reference book. That's that maximum capacity value where those curves, parabolas turn back. We know that the factor to adjust for driver population on weekdays, if they're all commuters, is 1.0. And we're likely to have commuters on weekdays. The lane width adjustment factor, and this table is not in your reference guide. In fact, I haven't seen it except in some of the textbooks there. But really, it says what's the key here is when we have lane width adjustment factors, we know that ideal conditions was 12 feet wide with no obstructions near the roadway. Okay. The problem says we had 10-foot wide lanes, so immediately that tells us that we've got narrow lanes and we're going to make some adjustments. It also went on to say that we had bridge abutments and other things that were within 2 feet of both sides of the roadway. And anything less than 6 feet is an obstruction. So we've got an adjustment for obstructions near the edge of the roadway. We simply go to a table to look up the lateral or lane width adjustment factor. We go down the table to a 10-foot lane. We go over to a 2-foot clearance on each side of the roadway, and the factor we would look up would be 0.85. So again, we're adjusting downward to account for lane width adjustments. And like I said, unfortunately, that table is not in your notes, but it is in some of the reference materials you might find if you're interested in this particular type of problem. So then the volume to capacity ratio, there in the middle of the page, is the service volume, 3,000 that we solved in Part B, divided by the maximum capacity times the number of lanes times these particular factors that we've calculated or looked up there. And it comes out to 0.977 of the ratio of the volume to the capacity. Okay. If we were to ask the question which level of service the freeway is operating, again, we could go to the table, or we could go back to that graph, and let's go to the graph if we could, because that's something that you have in front of you. If I go back to that graph and I go out to a volume to capacity ratio of 0.977, that's way out here to the far right of that graph, and I would see that we're operating probably in the range, we're in between K equals 42 and K equals 67, and that's going to be level of service E. Okay, and let me just put on this graph, this first point is level of service A, second point is level of service B, C, D, this should be E, and anything above that's going to be F there. We'll say this 0.977, that's something that's it's over the threshold for D, so that's going to be in the level of service E range at this point. I get that is an important point. If I got a value that was in between the threshold for A and B, I would describe that as level of service B, because it's over the threshold for A but less than the threshold for B. Now, in this particular problem, they went to a table and looked up and they found that the threshold for level of service D was 0.93, and we computed, remember, 0.97, so that's above that threshold, which would mean we're operating in the level of service E range. Okay. Now, if it goes down, question F in that particular series, again, is a very easy one. It says what would the volume to capacity ratio have to be in order to improve to the level of service to the next lower capacity level of service? We're operating at level of service E. If we wanted to get down to the next lower, would be D. And again, we could read from the chart or the table, and that threshold is 0.93, or choice D in that series. Okay. And I'm not going to go through all of the rest of the parts of this, because I think they're pretty much straightforward. If you can get just some of the basic concepts about capacity, volume to capacity ratios, and where these thresholds are for freeways. And again, I think this is a very common type of question that people see on exams of this type. It's very simple if you understand the concepts, and pretty straightforward to work through. If you're deciding to choose the highway questions for your to answer on the exam, you might want to see if you could borrow a copy of the Highway Capacity Manual. There's about a half a dozen tables that would be very beneficial for you to have copies of if you're going to work a problem of this type. But there's not that really half a dozen at the most, and you could work this problem and many more just like it.
Tell you what, if you got those tables?
Yes, I have those tables. And
give me those tables. I'll copy them, and we'll get copies to them, and we'll just append these notes.
Okay. Be glad to do that. Okay, that was for freeways. And there's actually different procedures for different types of facilities. Section 15 in your notes talks about signalized intersection capacity. And that's different from when we talk about signalized intersection capacity versus freeways, because now we have traffic signals along the roadway that are going to limit the roadway's capacity. And when we look at signalized intersections, what will depend on the number of factors we have to deal with, or that affect capacity, or the width of the approach, the number of lanes, the same as with freeways, whether or not we allow parking at the intersection, the directional distribution of traffic, what environment that we're in, the downtown central business district versus the suburbs, the heavy vehicles that we have in the traffic stream, the percentage of turning traffic, left and right turns will impact the capacity. Grade is not shown there, but that's another factor as well. Capacity at a signalized intersection can be computed by the equation in the middle of the page there. It's simply equal to this saturation flow rate, very similar to saturation flow on a freeway, multiplied by G over C, or the percentage or proportion of the time that the signal is green for that particular approach to the intersection. So if we looked at S in that particular equation, that would be very similar to the capacity of a freeway, where the signal is always green, and we simply have to adjust that number downward by the proportion of time that's available for that particular traffic stream. Now, in that particular equation, you'll note that there's two C's, lowercase c designating capacity, and uppercase C designating the length of the cycle at that particular intersection. The bottom part of that tells how we come about with with S, this ideal saturation flow rate. Because at a signalized intersection, we say ideal conditions are 12-foot lanes, level grades, all passenger cars, no buses, no turns, and the signal is always green. And if we could design traffic signals like that, we could all be very happy about it. But those factors out there are adjusting for the fact that the conditions aren't ideal. And they're very similar. They're primarily table lookup values, and there's a whole series in the manual. There's about 15 pages of tables that you can go to and look up the values for conditions that aren't ideal. Just very briefly, it says F sub W, that's a factor for width. F sub HV is a factor for heavy vehicles. F sub G is a factor for grades. F sub P is a factor for parking, because that affects capacity. F sub B, B is for bus blockage. A is for area type, whether you're in a downtown area or out in the suburbs. And then RT and LT are your factors to adjust for right and left turns that may be in your traffic stream there. Okay. So you can compute capacity for a signalized intersection. A level of service at intersections are based on the average delay to people that are using that intersection, and there's a rather lengthy equation based on queuing theory that's used to compute that average delay. Okay, and I can also provide that as an appendix to the notes, because I have seen a question or two about computing level of service at signalized intersections. I want to move on to section 16 and begin at least the discussion tonight on pavement design. I'm not going to get entirely through it tonight, but you may note from your outline that I'm on for an hour next week, and I think we'll get through enough of this to give you a good feeling for it. There's a lot of material in your notes on pavement design, but most of it is tables and figures and charts, and we won't spend a lot of time going through them because it's simply a matter of going to the right chart. When we look at pavement design, we're going to talk about standard truck loadings, and we're talking about separation distances between axles, what type of axles they are, whether they're single axle, dual axles, or whatever. And we're going to convert all loads on our pavement to axle loads or equivalent axle loads. For capacity analysis, we use passenger car equivalents. For pavement design, we'll use equivalent axle loads. And you'll note there on the right-hand side of that page are standard truck loadings, where we look at the different spacing between axles, both longitudinally and horizontally on our pavement surface, and the different configurations that we have. We also mentioned the different types of axles, single axle dual tires, and tandem axle dual tires as another way of classifying or converting axle loadings. Now you'll note from these two drawings we have a variety of spacings and axle types, and what we really want to do is to convert all of them down to some equivalent load that we can work with. Now, another thing that is mentioned in your notes in the middle of this section on pavement design or standard truck loadings is the concept of AASHTO design vehicles, and these are vehicles whose dimensions and characteristics that are used in design of roadways. And they talk about passenger cars, single unit trucks, buses, intermediate semi-trailers, large semi-trailers, and then the double trailer combinations. And depending on what type of vehicle that you expect, you would do certain things with your design. For example, if you expect large trucks to use that particular facility, you might design higher vertical clearances, larger radiuses around curves so they could turn easier, and things such as that, as well as a stronger pavement. Okay. I wanted to just mention that point. There's some standard truckloads that are used for design. When you look at this particular chart, which is on page 1613 in your reference book, these different load designations, and they depend on the loads on the different axle configurations and spacing between those axle configurations. And typically, what you will see in design manuals, for instance, in TxDOT's design manuals, they just say for certain types of roadways, they're going to design their bridges to withstand an H2044 load configuration. And that's what's outlined in this particular text. That's the equivalent truck that they're designing for on this particular types of facilities. So they have standard truckloads that are used for design. These are some typical ones that are used around the country.
F1 being the front axle.
F1 is generally the front axle. If I go back a couple of pages.
Yeah, it must be.
Yeah, if you go back to the start of 16, you'll see that F1 is the front axle, F2 would be the second one, and F3 would be the third axle. And those distances, D1 and D2, are the spacing between axles. And so you have different vehicle types, have different spacings for the different axle loads. The different pavement types, section 17 in your notes, we'll get into a little bit more detail about these different types. They talk about rigid pavements, and typically those are Portland cement concrete pavements. They can be pre-stressed concrete pavements or continuously reinforced, different types of concrete pavements. There's flexible asphalt, full depth asphalt, and deep lift asphalt, different types of design, but there's basically two different types, the rigid pavements and the flexible pavements, and different design philosophies and procedures for those two types of pavements. Typically the types of things that you need to know about these different pavements are some advantages and disadvantages of the different things, and those are pretty much laid out for you in your notes. And then there's some design procedures where they will give you a set of conditions and ask you to design a pavement based on those conditions, and they'll tell you which procedure to use. And we'll talk more about those design procedures next week, but I think you're pretty lucky in that your reference guide has the most complete set of different pavement design procedures of any textbook that I have seen, outside of one that specifically deals with pavement design. And even those books, typically there'll be one book for rigid pavement design techniques and another book for flexible pavement design techniques, whereas this reference guide has a pretty good overview of about the most commonly used 5 or 6 techniques in each procedure. Rigid pavements, some of the things that are mentioned there in your notes, there are some typical applications listed, some advantages and disadvantages of the rigid pavements, and typically they boil down to a couple of things. The rigid pavements or the concrete pavements generally are going to last for a longer period of time, and the disadvantage is that they typically cost more than the flexible pavements do. That's especially true in Texas, where we have a lot of petroleum products, and it's very cheap. If you go to some place like Australia, where they don't have petroleum, at least in the natural state, then concrete pavements become less expensive there. They can be reinforced or unreinforced pavements, and generally they're designed. AASHTO comes up with a set of design guidelines or specifications for calculating how much steel has to be in a particular pavements, and that's that steel, the amount of longitudinal steel, and that's the cross-sectional area, that's shown there. And AASHTO will also specify the spacing and the sizing for the steel dowels that are in reinforced pavements. Again, when we get into flexible asphalt concrete or flexible pavements, typical uses, they're generally for, as I mentioned, they're going to be cheaper than concrete pavements. You'll find them generally used for lower volume facilities, higher volume facilities, high speeds. You'll find concrete pavements, lower volume, low speeds. You'll find more asphalt pavements. In Texas, we use a lot of asphalt pavements for even some of our high volume state highways as well. Again, your book lists advantages, disadvantages, and typical uses. What I would suggest to you is maybe to go through and highlight what some of those key elements are in your notes in terms of advantages, disadvantages, and typical uses. Because I have seen questions where they ask you what are the advantages, 3 advantages of flexible asphalt concrete, or 3 disadvantages of flexible asphalt concrete. Asphalt binders, some things that again are in your notes, talking about the use of asphalt binders or other things to tie it together rather than, or hold the pavement together rather than the petroleum products. The intent to become less dependent on imported oil, looking at sulfur content, maybe adding silicone for workability. There's some standard equipment that you can use and maybe even get a better quality pavement. Some of the things that are being used now are crumb rubber in pavements as well. And when you get into actually using some of these things, and I'm nearing the point where I'm going to stop today, when we start looking at pavement design, we start talking about really how thick the pavement has to be. And we're going to talk about, and I notice a spelling error on this particular slide, but we'll talk about the base, the sub-base, and then the pavement surface itself. And for each of these layers of the pavement, there's certain minimum thicknesses. And what we're really talking about there is there's a minimum value that for constructability we really can't go below and have a realistic a layer of asphalt any thinner than about 1.5 to 2 inches. And we can go above that relatively easy, but we can't have something that's any thinner than that. And for cement, lime, asphalt treated bases and sub-bases, about 4 inches is as thin as we could go in terms of a layer. I'd like to get one more slide before we stop tonight, just to introduce the concept in terms of pavement design parameters here, and it's label 20. We talk about these different layers, and what we're really going to need to know in order to design a pavement is how strong each of these layers are. How strong the asphalt or the concrete is, how strong the sub-base, the base, the subgrade material is, because it's got to support a load of traffic that's going to be moving over that particular facility. So we've got to know something about the properties of the material, the different materials that are available to us, and where we're going to be building that particular roadway. Because we do it differently in Texas than we do in the northern part, where we have lots of really bad weather. We also need to know something about the load that we're going to have to support, the number of vehicles, the number of heavy vehicles. So we want to convert our traffic stream to equivalent axle loadings. Capacity analysis, we converted everything to equivalent passenger cars. For pavement design, we're going to convert everything to equivalent axle loads. And next Wednesday, excuse me, you'll see me talking about what they call EASLs, equivalent axle single loadings is the acronym, and I'll show it to you next week on that. So we convert everything to equivalent axle loadings, and then we have to predict traffic growth, and we'll use some equations that you do for uniform growth rates. The same equations that you use for economic analysis we'll use for predicting how much traffic is going to grow over a 20-year period. So let me I think stop there, and as far as I'd like to get tonight, see if there's any questions that I can answer at this point, and we'll go more into it next week.
Okay, John, your turn.
No questions. I'm going to be on